All right, so in Chapter 3, Section 2, we're going to be talking about quadratics. So we are going to do a whirlwind review of what we would have talked about in the previous class. So if you just took Math 121, we're basically going to review pretty much Chapter 8 in one section. So a quadratic equation is in standard form if it has the form ax squared plus bx plus c is equal to 0. So the key thing we want to note here is that in standard form, the equation has 0 on one side. The next property we want to remind ourselves of is the zero product principle, or the zero product rule. If a times b is equal to 0, oh, hold on, I'm getting ahead of myself. If a and b are any algebraic expressions, and a times b is equal to 0, then a is equal to 0 or b is equal to 0. So that's our zero product rule, which basically says if we multiply two things together and get 0, then at least one of those two things has to be 0. All right, we're going to use that to help us resolve example number 1. So we wish to solve this equation. So the first thing we need to do to resolve a quadratic equation is we need to put it in standard form. So standard form says that we need to have 0 on one side of the equation. So our equation is 6x squared minus 16x equals negative 10. So we add 10 and we add 10, and that gives us 6x squared minus 16x plus 10 is equal to 0. So we've now successfully put our quadratic equation in standard form. So then step 2 is we need to factor. So first thing we always look for when factoring is a GCF, if there is one. And in our case, we have a GCF of 2. So if we factor out our GCF of 2, that would leave behind 3x squared minus 8x plus 5 is equal to 0. We're still not done factoring, so in this case, we need to use either guess and check, or the AC method, to do our factoring. So I'm going to write out the AC method, but if you know the guess and check method and like to use it, that's perfectly fine. Either one is okay. So for our AC method, our quadratic, we have our A, our B, and our C. In this case, our A is 3, our B is -8, and our C is 5. So A times C is 3 times 5, which is 15. We need to find factors of 15 that add up to -8. Well, in that case, it's going to be -3 times -5 is positive 15, and -3 plus -5 is equal to -8. So we're going to rewrite our -8 as 3 and 5, so that gives us our GCF is 2 is still on the outside. We have 3x squared, and then we're going to have minus 3x minus 5x plus 5 is equal to 0, and then we factor by grouping. So this is our group 1, and this is our group 2. So we factor our GCF out of group 1, leaving behind, so our GCF in our first group is 3x, and then that leaves behind an x take away 1, and our GCF in group 2 is -5, and that leaves behind an x minus 1. And we have our common binomial factor of x minus 1 that we factor out. So we have our 2, our common binomial factor of x minus 1 we factor out, and then it leaves behind the 3x minus 5, and all of this is still equal to 0. So now, after factoring our quadratic trinomial, we finally use the zero product rule. So we have our A and our B. So we have A equals 0 or B equals 0. So in this case, x minus 1 is 0 or 3x minus 5 is 0. So to solve each of these, we add 1, we add 1. We get x equals 1, or we add 5 and we add 5, and we get 3x equals 5. Divide by 3, divide by 3, and we get x is equal to 5/3. And those would be our two solutions to that quadratic equation. So let's take a second and so for example number 2, we wish to solve. And we'll notice that this one looks a little different than the problem that we just did. So we have a perfect square. This won't happen all the time, but if it does, there is a different method that we can use, which is the square root property. So the square root property states the following: if A is any algebraic expression and a squared is equal to b, then a is equal to the negative square root of b, or a is equal to the positive square root of b. It's worth noting this is often written as a equals plus or minus the square root of b. So that's just a shortened way to write the same thing. Well, we have a perfect square up here. So if we look, our a in this case is going to be x minus 4. So we have something in exactly the form a squared is equal to b. So then our solutions are a equals the negative square root of b, and our b is going to be negative 5, and a equals the positive square root of b. So in our case, it's going to be x minus 4 is equal to the negative square root of negative 5, and x minus 4 is equal to the positive square root of minus 5. From our previous section, we know that this can be simplified. The square root of negative 5 is the same as negative 1 times 5. And what is the square root of negative 1 the same as? Well, that's the same as I. So we get x minus 4 is equal to the square root of 5, I, and x minus 4 is equal to, sorry, I'm missing a minus sign. Same thing here, we're going to get the square root of 5 and I. So then we can solve this by adding 4 to both sides, and we get a complex numbered solution, 4 minus the square root of 5i. And we add 4 and we add 4, and we get x equals positive 4 plus the square root of 5i. And that is our solution, or solutions, plural, to this equation. And just like what we did in the previous problem, we can actually check our solution. We have x minus 4 squared equals negative 5. Well, I know x is equal to 4 minus the square root of 5i. So let's type that into my calculator and see what happens. So x is 4 plus the square root of 5. Don't forget to pop out of your square root, I, take away 4, squared. And if this is a solution, what should I get when I press enter? Negative 5, right? And indeed I do. So I can check that my solution is indeed correct. And if you plug in the other solution, which I'm not going to do, you will see that you get exactly the same thing. So U-try number 1 is already set up for us to use the zero product rule. So we have our a times b equals 0, and that gives us a equals 0 or b equals 0. So in this case, our a is 5x minus 7 equals 0, and our b is 3x plus 4 equals 0. So we add 7, we get 5x equals 7. Divide by 5, divide by 5. So our first solution is x is 7/5. And in our second equation, we minus 4, and we get 3x equals negative 4. Divide by 3, and x is negative 4/3. For our second one, we need to use the square root property. It's worth noting, if you distribute this out, collect all your like terms, set it equal to 0 and factor, you're going to get the same answer. It'll just take you 5 times as long. Using the square root property is much faster in this case. So we minus 1, and we have x plus 3 squared equals 8. We divide by 2, and we get x plus 3 squared is equal to 4. So now we can identify our a and our b, and by the square root property, we have a equals the negative square root of b, or a equals the positive square root of b. So we get x plus 3 equals the negative square root of 4, or x plus 3 equals the square root of 4. The square root of 4 is just 2, so we get x plus 3 equals negative 2, or x plus 3 equals positive 2. So we minus 3, we get x is negative 5. We minus 3, we get x is negative 1. So either way, we get this. So as mentioned, if you distribute all of that out, collect your like terms, and do all of that stuff, you will get exactly the same answer when you refactor and use the zero product rule. It's a lot longer, but remember what I said, I am goal-oriented, not path-oriented. Although we don't want to spend way too much time doing something that can be done much more efficiently in a different way. All right, let's take a look at our next example. So example 3 says use the graph to find the x-intercepts and the zeros of the function. So this is exactly the same thing that we did back in chapter 1, section 5. And just to remind us of our definition, a zero of a function is an input such that the output is equal to 0. This is the same as the ordered pair c, 0, which is actually the x-intercept. And we take note that zeros, solutions, and x-intercepts are the same point. And when we have them graphically, back in 1.5, the x-intercepts are where the graph crosses the x-axis. Those are the same thing as the zeros. So nothing has changed. Fast forward back to chapter 3, section 2. We look at our graph, and in our graph we have two x-intercepts. And those are at the ordered pairs 3, 0, and 7, 0. So then the zeros are x equals 3 and x is equal to 7. So as we see from the graph, we have 1, 2, 3 x-intercepts, and they're located at -7, 0, 1, 0, and 5, 0. So the zeros are x equals -7, +1, and 5. Because the zeros are the inputs when the output, or the y coordinate, is equal to 0. All right, so for our next one, we're going to skip example 4 and go directly to u try 4. And I'm going to do u try 4. So completing the square is a wonderful tool, but it is a terrible way to solve quadratic equations. So we're going to talk about some other methods to do so. So I don't really want you to use completing the square to solve anything, but I do think we need to see it and help us understand what it is. So let's start with the idea of what completing the square is. So completing the square has its origins in ancient Greece. So I'm going to color code these things. So I'm going to have my x squared. I'm going to have my negative 6x. And then I'm going to have my 18. So to complete the square, I'm going to minus 18 from both sides, which doesn't put this in standard form, and leaves me with x squared minus 6x is equal to negative 18. And as I mentioned, this has its origins in ancient Greece. So they were very good geometers. So instead of visualizing x squared as an algebraic entity, they visualized it as a square that had side length x. Then its area, x times x, would be x squared. Similarly, negative 6x would be visualized as a rectangle with width negative 1 and height x. So it would have area negative x, and I would need to have 6 of these. And lastly, 18 or negative 18, they would be visualized as 1 by 1 squares, and I'm not going to draw all 18, but there would be 18 of them. And the reason this algorithm is called completing the square is we want to build the biggest square that we can out of our available pieces. So if I were to try to build a square, the thing that makes something a square is it has the same length and the same width. So I would start by putting my square here. And if I want to build something that's a square, it needs to have the same base and the same height. So would I be able to put one blue rectangle on the right side and 5 blue rectangles down? No, because that would make a rectangle and not a square. So the key idea is I would have to put 3 and 3. So if I put 1, 2, 3 of them here, and 1, 2, 3 of them here, that leaves something that looks like this. Then I have this piece that is missing. This is my missing square. And the square that is missing has area 1, 2, 3, 4, 5, 6, 7, 8, 9. And we'll notice something interesting. Each of these widths right here, since I put 3 of them, are negative 3 and negative 3. So that makes this entire side length of the square x minus 3, and this is also x minus 3. And my missing square is going to be negative 3 times negative 3. It has area 9. So that's what is missing from this square. So now I have my equation, which is x squared minus 6x is equal to negative 18. Well, I'm missing a square of area 9. So if I add 9 pieces to this side, I would have to add 9 pieces to this side. This is a perfect square trinomial. And if I factored it, what are my factors of positive 9 that give me negative 6? Well, it's negative 3 times negative 3, which is what we see over here. This perfect square is actually geometrically the square we built over here. It has side length x minus 3, and x minus 3 is equal to, well, if I added 9 more pieces to my negative 18 over here, I'm going to have negative 9. After I've completed the square, we'll notice that this thing is in the perfect form. I could use the square root principle. Because if I have x minus 3 squared equals negative 9, here's my a and here's my b. So using the abbreviated version, if I had the square root of x minus 3 squared is equal to the square root of negative 9, that would give me x minus 3 is equal to plus or minus, well, that's negative 1 times 9. Square root of 9 is 3, and the square root of negative 1 is I, so I get plus or minus 3i. So I add 3, and I get x is equal to 3 plus or minus 3i. And that would be my two solutions to that equation. Interesting, right? So we can use the square root property to solve quadratic equations. So our goal is we want to solve the general quadratic. Well, if we have our general quadratic is ax squared plus bx plus c equals 0, if I can solve this for any numbers a, b, and c, I've then solved every quadratic equation. The key to do this is completing the square. So we're going to follow the process like what we did above. So the first thing we're going to do is minus c from both sides, and that gives us ax squared plus bx is equal to negative c. Then we're going to divide by a, and divide by a. This gives us x squared plus b over a x is equal to negative c over a. So then the next thing we did is we needed to find the part of our square that was missing. So we took half of our b term, and we'll notice that here each of these lengths were 3 and 3 respectively, which was half of our b term. So the missing square is b over 2 squared. So fast forward back to here, this is our new b term. So we need to take half of b over a, so b over a over 2, which we'll write as a fraction as 2 over 1 and square it. So that's b over a times the reciprocal of 2 over 1, which is 1/2 squared. So that's b over 2a squared, so we get b squared over 4a squared. This is what we're going to need to add to both sides of that equation. So we have x squared plus b over a x, and then we're going to add b squared over 4a squared, but if I do it to one side, I have to do the same thing to the other, and then minus c over a. So we need to keep simplifying. So over here on the right side, we need a common denominator. I have 4a squared and a, so this is missing a 4a, and this is missing a 4a. And then this guy, we need to factor. So if we go back to our diagram once again, we noticed that we put half of these here and half of these here. That told us what the side length of our square was. So our side length was x minus 3, because we had our x and then we put half of these things, so this is b over 2. So using that same pattern, this is going to factor into x plus b over 2a squared is equal to b squared minus 4ac all over 4a squared after we get our common denominator. So then we use our square root principle by taking the square root of both sides, and we get x plus b over 2a is equal to plus or minus, and then we have the square root of b squared minus 4ac, all divided by the square root of 4 is 2, and the square root of a squared is a. So then we minus b over 2a, and we minus b over 2a, and that gives us x equals, and these already have a common denominator, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So now this last part we do want to write down. This is the quadratic formula. We can use it to solve any quadratic equation. So to solve ax squared plus bx plus c equals 0 for a not equal to 0, x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And this is the quadratic formula. So to solve this using the quadratic formula, the first thing we need to make sure of is it must be in standard form. So well, in this case, there's nothing to do. We're already done. It's in standard form. So 9x squared minus 6x plus 46 is equal to 0. Then step 2, we need to identify a, b, and c. So in our case, we have our a is 9, our b is negative 6, and our c is the number 46. And then 3, we're just going to use the quadratic formula. So our solutions are x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in our case, we have minus a minus 6 plus or minus the square root of b squared, so negative 6 squared minus 4 times a times c all over 2 times a. So we start simplifying. A minus minus 6 is positive 6 plus or minus. If I grab my calculator, I can simplify the radicand. So negative 6 squared minus 4 times 9 times 46 gives me 1620, or negative 1620 rather, all over 2 times 9 is 18. So now we need to simplify the square root of negative 1620. If we just type it into our calculator, it's going to give us a decimal approximation, which is okay, but we're going to need an exact answer. So we know since it's negative, it's going to be the square root of positive 1620 times I, because this is imaginary. But now we need to simplify this. And if we remember, on our calculator, we can use it to help us extract the largest perfect square from 1620. So we go y equals, and we go 1620, and then we divide by x squared, and then we make our table. So we need to scroll down until we find the largest whole number in our y column. And we know we can stop scrolling down whenever y gets less than 2. So I scroll down, okay, I'm here, and I need to go up until I find my first whole number entry in my y column, which is here. So this tells me then what we found This says that the square root of 1620 is equal to 18 times the square root of 5. Because this was our perfect square, so in other words, the square root of 1620 is the same as 18 squared times 5, and you can double check that. If we check that on our calculator, 18 squared times 5 does give us the 1620. So the square and the square root undo each other, so we get just the 18, but the 5 doesn't simplify, stays inside. So now we get 6 plus or minus 18 square roots of 5i all over 18. So this is 6 over 18 plus or minus 18 square roots of 5i over 18. The 18s reduce out here, and 6/18 will reduce to 1/3 plus or minus the square root of 5i. And that would be our two solutions to that quadratic equation. All right, so let's go ahead and resolve this. So it's already in standard form, and we can identify our A, our B, and our C. So our A is 1, our B is -6, and our C is 18. So then that would give us x equals a -6 plus or minus the square root of -6 squared minus 4 times 1 times 18, all divided by 2 times 1. So then that would give me 6 plus or minus, and I grab my graphing calculator, and I would have -6 squared minus 4 times 1 times 18, which gives me -36, so plus or minus -36 all over 2. And that one's a perfect square, so it would work out in our calculator. So if I go second square root, I get 6i. So I get 6 plus or minus 6i all over 2. So that's the same as 6 over 2 plus or minus 6i over 2, so 3 plus or minus 3i. And that would be our solution to that quadratic equation. All right. So before we do our last one, we need to draw a little bit of a diagram here. So what we want to talk about is the discriminant. And the discriminant is the part of the quadratic formula that's underneath the radical. So the b squared minus 4ac. And the discriminant tells us about the number and type of solutions to a quadratic. So we really have three possibilities, as we talked about before. B squared minus 4ac can be a positive number. B squared minus 4ac can equal to 0, or the last case is b squared minus 4ac can be less than 0. So those are our three possibilities. If b squared minus 4ac is greater than 0, we're going to have two real solutions. If b squared minus 4ac is equal to 0, we're going to have one, and they sometimes call it a repeated, real solution. And if b squared minus 4ac is less than 0, we're going to have two imaginary solutions. So the discriminant, or b squared minus 4ac, tells us about the number and type of solutions to any quadratic equation. So if we take a look at example number 6, we want to find the discriminant, so b squared minus 4ac, and then determine whether we have one real numbered solution, two different real numbered solutions, or two different imaginary solutions. So we need to identify our a, b, and c, so we need standard form. And once again, standard form, we're done, and then 2, we need to identify a, b, and c. So our a is 25, our b is 20, and our c is 4. And now we calculate b squared minus 4ac. So b squared minus 4 times a times c is going to be 20 squared minus 4 times 25 times 4. So we calculate this, 20 squared minus 4 times 25 times 4, and we get 0. So then we come up and we look at our thing. So if we get 0 for b squared minus 4ac, that means we go down our middle path. So our solution is that we have one repeated real solution. So we have one real solution. So the discriminant problems are pretty straightforward.